Hello, hello everybody. How are you? Hope you are doing well. So today we continue with our classes, and we discuss about lecture 7, describing the data. So we have discussed in previous lectures about how we conduct a survey and how we gather the data. And now the next step is to organize and summarize and describe this data. For today's lecture, we are going to review strategies that we can use to effectively organize, summarize, and describe our data. And descriptive statistics, we will intend to provide a brief review of these statistics. As you know that there is mostly 3 types of data. So we have the primary data, where we go to the field and collect the data, and we know how to do that, and we have also talked about the questionnaire. Secondary data has 3 types. We have the time series data, where we have only one country or one company or one firm, but we have several years of data. And the second one is cross-sectional data, where we have so many companies to be investigated or so many countries, but we have only one time or 1 year or 1 month of the data collected in only one time. And the last, we have panel data, where we have a combination between the time series and cross-section. Means we have many countries or many companies at the same time. We will have so many years. So as I say, the data are ordered by time for time series, and the time series data is a set of observation of the values that a variable takes at different times. Such data may be collected at regular time interval, daily, weekly, monthly, quarterly, or annually. An example of that, consumption and disposable income for Malaysia from 1990 to 2013. Cross-sectional data also, as I described just now, is data that is characterized by individual units. So the units may refer to people, companies, sector, or countries, and cross-sectional data are data collected on the same point in time. An example, consumption and disposal economic of different Asia countries in 1990. And the panel data is, or you call it also pool data, a set that have both time series and cross-sectional component. An example, consumption and disposal income among Asian countries, Malaysia, Singapore, Thailand, and Indonesia for the period of 1990 and 2013. So while collecting the secondary data, means the data which is not collected by you, or by you, but you collected from a second source, you should consider the following. The first thing you have to see, does the data have to answer the question set out in the problem statement? Is the data really match to your research objective? Does the data apply to the time period of your interest? If the data is outdated, you may not use it. Does the data apply to the population of interest? If you are doing about Asian countries, as we say now, but you have data about European countries, is not matching. do the other terms and variable classification present and apply, and are the units of measurement comparable, the measurement of your variable. If possible, also you go to the original source of the data and check the reliability and validity of the data. Is the cost of the data acquisition worth it or no? If it costs you hundreds of thousands but does not provide full information, so it is not feasible. Is there a possibility of bias? And can the accuracy of the data collection be verified? So these are the questions that usually need to ask, but particularly when we collect secondary data, especially from very well-known organizations like World Bank, United Nations. So most probably that data is really reliable and valid. So now before we go to the inferior data analysis, we have to do some descriptive statistics to understand our data. So descriptive statistics allow you to summarize the properties of an entire distribution of scores with just a few numbers. So although descriptive statistics are commonly used to address the specific questions that you had in mind when you design your study, they also can be employed to help you discover important but perhaps hidden patterns in your data that may shed additional light on the problem you are interested in resolving. So the research or the search for such pattern in your data is termed as exploratory data analysis or EDA. When research has been designed to answer a specific question or set of questions, there is a strong temptation to rush directly to the inferential statistical techniques that will assess the statistical significance of your finding and to request only those descriptive statistics related directly to the analysis. So this such group means standard deviation and standard error. So some exploratory techniques help you spot serious defect in your data that may warrant taking corrective action before you really proceed to your inferential analysis. So others also, it may help you to determine which summary statistics would be appropriate for a given set of data. Still others also may reveal unsuspected influences. So we are going now to introduce a number of descriptive tools, both numerical and graphical, for describing data and revealing the secrets that behind within these data. What are the steps that we need to use in EDA? First, as we say, we organize and summarize data on data coding sheet. Then if desired, we organize the data for a computer entry. Then we graph the data using bar graph, histogram, line graph, or scatter plot to that distribution can be visually inspected. And last, this will help choose the appropriate statistic. We display frequency distribution on histogram and create a stem plot. We examine the graph for normality or skewness on distribution. So organizing our data. So before you can interpret your data, you must first organize and summarize them. How you organize Your data depend on your research design, whether you have conducted a survey, observational study, or experimental study. How many variables were observed and recorded, and how observations were grouped or subdivided. So a few representative example we follow. For example, for the survey data, the data sorry, the data summary sheet would be appropriate. The data are organized into a series of columns, one for numbering the respondent, one for each question asked, and one for each demographic items, to save space. The identifier over the column would be kept short. For example, in here, a certain demographic variables can be a dummy coded, example 1 or 2, or yes 1 and no 0. A K or a code sheet, would be prepared to describe, the scale used for questions. Then experimental or quasi experimental data design break down the dependent variable according to treatment or categories. You can organize data from these designs into two distinct ways. One way called an stacked format is to create separate column for the score from each treatment. The second way to organize your data is to use a stacked format. In this format, you create one column for the participant IDs, a column for the treatment level, for example, dummy coded, and a column for each dependent variable. So this is an example, of the unstacked and stacked table. You can see here they're almost particular similar, but I have some differences, in the way of presentation. Then we go to examining the data. So typically the data from individual groups or coordinations are used to compute summary statistics such as group, the average that represent group or condition as a whole. When you calculate an average, you have one score that characterizes an entire distribution. You then can refer to the performance of subjects in a group by citing the average performance. If your data will be submitted to the statistical analysis based on treatment means, you will be treating your data in this way. So although convenient, group average do have two important limitations. First, the average score may not represent the performance of individual subject in a group. For example, an average score of 5 can result if all 10 subjects in the group score 5, or if half score 0 and half score 10. In the former case, the average accurately reflects the individual performance of each subject. In the latter case, it does not. So we examine this idea in more details during the discussion of the mean later. Unfortunately, researchers too often fall into the pattern of collecting data and then calculating an average without considering the individual score constituting the average. A good strategy to adopt is to look at both the group and individual data. When you have repeated measures of the same behavior, examining individual data shows how each subject performed in your study. This may provide insight into the psychological process being studied that are not afforded by grouping data. When you collect only a single score for each subject, you should still examine the distribution of individual scores. This usually entails plotting the individual score on a graph and carefully inspecting the graph. So, graphing the data. Graph represent a data in two-dimensional space. We have two dimensions are defined by two lines intersecting the right angles called the axis of the graph. Horizontal axis is called the abscissa or the axis. Levels of the independent variables are represented along the axis. Vertical axis is called the ordinate or the y-axis. Values of the dependent variables are represented along the y-axis. A pair of values, one from the x-axis and one from the y-axis, define a single point with the graph. So we have, for example, the first type is a bar graph where represent data as bars, extending from the axis representing the independent variable. Length of each bar reflect the value of the dependent variable. The width of each bar has no meaning. A precision of the estimate is shown in the error bar, or we call it whiskers extending at the top of each bar. Also can be used to represent data from a single factor or a multi-factor design. Works best when the independent variable is categorical. Then we have a line graph represents data as a series of points connected by a line. The most appropriate when the independent variable is continuous and quantitative, used to display functional relationships. Line graph also can predict different shapes, or can depict different shapes. Positively accelerated curve starts flat and becomes progressively steeper as it moves along the x-axis. Negatively accelerated, the curve is steep at first and then level off as it moves along the x-axis. Once the curve levels off, it's said to be asymptotic. So this is one of the line graph. Can vary in complexity. We have a monotonic function represent a uniformly increasing or decreasing functions. A non-monotonic function has a reversal in direction. Then a line graph can also vary in complexity. We have a monotonic function represent a uniformly increasing or decreasing function, and we have a non-monotonic function has revealed in direction. So we can see here positively in the left and negatively in the right accelerated function. So this is in the left is positively and this is negatively. And we have also here a non-monotonic function relationship, goes up, then down, goes up. Then we have also the scatter plot. So the scatter plot used to represent data from the two dependent variables. The value of one dependent variable are represented along the x-axis, and the values of the other dependent variables are represented along the y-axis. May include a best fitting straight line that indicate the general trend of the data, and coefficient or correlation and the equation for the line are usually shown in this case. So we have, this is the scatter plot. We can have a line, for example, here could be like that. Yeah, could be like that. Then we have a pie graph used to represent a proportion or a percentage. We have two types, standard pie graph and exploded pie graph as shown in this graph. The left is standard pie graph and the right is exploded pie graph. What is the importance of graphing the data? So you can use either tables or graph to summarize your data. If you organize data in tables, you present the numbers themselves, average and all row score distributions. If you display the data in a graphical format, you lose some of this numerical precision. The value of a point usually can only be approximately by its position along the y-axis of the graph. However, graphing data is important for two major reasons. First, showing relationship clearly. The saying, one picture is worth of 1,000 words could be applied in graphing data. Although summarizing data in table is fine, a proper graphing adds a degree of clarity no table can provide. So the graph brings out subtleties in the relationship that may not be apparent from inspecting a table. A second, choosing appropriate statistic in addition to making it easier to see relationship in your data. Graphs allow you to evaluate your data for an application of an appropriate statistic. So before you apply any statistic to your data, graph your sample distributions and examine these shapes. Your choice of statistic will be affected by the manner in which scores are distributed. Graphing also your data on a scatter plot is helpful when you intend to calculate a measure of correlation. Inspecting a scatter plot of your data can also help you determine which measure of correlation is appropriate for your data, what you would look for, and how your finding would affect your decision are taken up during the discalculation measure later. The frequency of distribution. One of the first steps to perform data when analyzing your data is to create a frequency distribution for each dependent variable in experiment or for each variable in correlation study. A frequency distribution consists of a set of mutually exclusive categories or classes into which you sort the actual values observed in your data together with the amount of your number of data, the values falling into each category of frequencies. Then classes may consist of response categories, for political party affiliation. They may consist of Democrat, Republican, Independent, and others, or ranges of score values along quantitative scales. For example, IQ, they may consist of 65 to 74, 75 to 84, and so on. So we have here some type of graphs or that or can be used. For example, we have histogram resembles a bar graph. Bars are drawn that seem to indicate that there are no gaps between adjacent classes. The y-axis represents a frequency scale on which the variable was measured appears along the axis. So this all we can graphically frequency distribution will be shown on that histogram. So here this is the shape of the histogram. So in this figure, display our IQ frequency distribution, for example, as an histogram. Histogram resembles bar graph with each bar is representing a class. Unlike the bars in a bar graph, those in an histogram are drawn touching to indicate that there are no gaps between adjacent classes. Although on an histogram, the y-axis represents the frequency, a count of the number of observations falling into a given category, for example, a number of exam scores falling into the categories of A, B, C, D, or F. On a bar graph, also the y-axis typically represent, the mean score. The scale on which the variable was measured appears along the x-axis with bars positioned appropriately to cover their respective ranges along the scale. Then the y-axis denotes the frequency. Thus, a given bar's length indicates the frequency of the score falling within this range. An histogram appearance changes depending on how wide you make the classes. Make the classes tunerable and you produce a flat-looking histogram with many empty or nearly empty classes. Make the classes too wide and you will produce a tall histogram lacking in details. The goal is to create a histogram that indicates the shape of distribution, one that is neither too wide and flat nor too narrow and tall. So this is here an example. The A here is a positively skewed histogram and B is negatively skewed frequency distribution. And here we have bimodal frequency distribution. It looks like that, or bimodal frequency distribution. Then we go to stem plot. So as a quick alternative to the histogram, you may also consider using a stem plot, or also known as a stem and a leaf plot. To create a stem plot of your data, you simply break each number into two parts, stem and leaf. The stem part consists of leftmost number or numbers and the left and the leaf, the rightmost number. Those on IQ score of 67 would be broken into its leftmost number or stem 6 and rightmost number or leaf 7. Let's see, for example, here we have this example, after finding the lowest and the highest stem, make a column that includes all the stem numbers in ascending order from lower to highest. Then draw a vertical line immediately to the right of the stem column. Finally, for each score in your data, find its stem number in the stem column. Then write its leaf number on the right of the vertical line on the same row as the stem. So as we say, if the IQ score is 67, would look like the first entry at the top of the figure here will be here 6 for the stem and 7 for the leaf. You do this for each number in your distribution. The final result will look like something like this, okay, which plots some hypothetical IQ data as a stem plot. A stem plot are easy to construct and display and have the advantage over histogram and tables of presenting all the actual values present in the data. However, you do not have much freedom to choose the class width because stem plot inherently creates class width of 10, the span of the stem. Stem plot are not especially useful for larger data sets because the number of leaves become too large. So the measure center. A measure of center, also known as a measure of a central tendency, gives you a single score that represents the general magnitude of score in a distribution. So this score characterizes your distribution by indicating a score value that falls at or near the middle of the distribution. The most common measures of the center are the mode, the median, the mean, also called the arithmetic average. Each measure of the center has strengths and weaknesses. Also, situation exists in which a given measure of center cannot be used. So the first one is the mode, where the mode is simply the most frequent score in a distribution. To obtain the mode, count the number of scores falling into each frequency category. The response category with the highest frequency is the mode. The mode of the distribution 1, 2, 4, 6, 4, 3, 4 is 4 because 4 is the most frequent score. Then we have the median. So the median, the second measure of the center, which is a middle score in a distribution. To calculate the median, follow this step. First, order the score in your distribution from the lowest to higher, or higher to lowest, it does not matter. Count down through the distribution and find the score in the middle of the distribution. This score is the median of the distribution. What is the median of the following distribution? For example, 7, 5, 2, 9, 4, 8, and 1. The correct answer is 5 because we have to rearrange the order and become 1, 2, 4, 5, 7, 9, 8, and 9. And 5, number 5, is the middle score. But you may be wondering what to do if you have an even number of score in your distribution. In this case, there is no middle score. So to calculate the median here with an even number of scores, you order also the distribution as before and then identify the two middle scores. The median is the average of these two scores. For example, with the ordered distribution 1, 3, 6, 7, 8, and 9, the median is 6.5 because we will take the median 6 plus 7 equal 13 divided by 2 and equal to 6.5. The median takes more information into account than the mode. However, it is still a rather insensitive measure of center because it does not take into account the magnitude of the score above and below the median. As with the mode, the two distributions can have the same median and yet be very different in character. For this reason, the median is used primarily when the mean is not a good choice. So now we talk about characteristics of the mean. So the mean denotes as M is the most sensitive measure of a center because it takes into account all scores in the distribution when it is calculated. It is also the most widely used measure of center. The compositional of a formula for the mean is M equal the sum of x divided by n, where the sum of x is the sum of scores and n is the number of scores in the distribution. So to obtain the mean, simply add together all the scores in the distribution and then divide by the total number of scores, which is m. The major advantage of the mean is that, unlike the mode and the median, its value is directly affected by the magnitude of each score in the distribution. However, this sensitivity to individual score values also makes the mean susceptible to the influence of outliers. One or two such outliers may cause the mean to be artificially high or low. So your job as a researcher is to identify those outliers and remove them from your data. So measure center application, as we say now, we have three. So we have the first one is the mode used if the data are measured along the nominal or an ordinal scale. We have the median used if the data are measured along an ordinal scale and if interval data do not meet requirements for using the mean. And the mean used if data are measured along an interval or ratio scale and if scores are normally distributed. Most sensitive measure of centers and does not represent the center if distribution is skewed. So here you can see we have three graphs. The first one, in my left, is the normal one. The A is also we have location of mean, median, and mode in a normal distribution, left, and is positively in A and negatively in B. Negatively skewed distribution. So we have three. You can see in the left one, all the mean, median, and mode are normally distributed. But in the right side, we have A, which is positively skewed distribution, and B is negatively skewed distribution. So now we talk about a measure of spread. So another important description or descriptive statistic you should apply to your data is a measure of spread, or also known as a measure of variability. If you look again at some of the sample distribution described thus far, you can notice that the score in the distribution differ from each other. When you conduct an experiment, it is extremely unlikely that your subject will all produce the same score in your dependent measure. A measure of a spread provides information that helps you to interpret your data. Two sets of score may have highly similar means, yet a very different distribution. As the following example, for example, imagine that you are scored for a professional baseball team and are considering one of the two players for your team. Each player has 0.263 batting average over the 4 years of college. The distribution of the two players' average are as follows. The first player is 260, 397, 200, 195, and the second player is 263, 267, 259, and 263. Now, which of these two players would you prefer to have on your team? Most likely you would pick player 2 because he is more consistent than player 1. But this simple example illustrates an important point that descriptive statistics. When you are evaluating your data, you should take into account both the center and the spread of the scores. So here we are going to review 4 measures of spread: the range, the interquartile range, the variance, and the standard deviation. First, we start with the range. The range is the simplest and the least important measure of spread. To calculate the range, you simply subtract the lowest score of the highest score, and In the baseball example, the range for player 1 is 0.202 and the range of the player 2 is 0.008. The two problems with the range are that it does not take into account the magnitude of the scores between the extremes and that it is very sensitive to outlier in the distribution. So if you compare the following two distribution scores 1, 2, 3, 4, 5, 6 and 1, 2, 3, 4, 5, 31, the range of the first distribution is 5 and the range of the second distribution is 13. The two ranges are highly discrepant despite the fact that the two distributions are nearly identical. For those reasons, range is rarely used as a measure of the spread. So we go for the interquartile range. It is another measure of the spread that is easy to calculate. To obtain the interquartile range, follow this step. First, order the score in your distribution. Divide the distribution into 4 equal quarters. Find the score separating the bottom 25% of the distribution as quartile 1 or Q1. Then the score separating the top 25 as Q3 from the rest of the distribution. The interquartile range is equal to Q3 minus Q1. The interquartile range is less sensitive than the range of the effect of extreme scores. It also takes into account more information because more than just of the highest and the lowest scores are used for its calculation. So the interquartile range may be preferred over the range of institution in which you want to relatively simple rough measure of a spread that is resistant to the effect of skew and outlier. Then we have the third one is the variance. The variance or S square is the average square deviation from the mean. The defining formula is S square equal the sum of x minus m all power 2 divided by n minus 1. So where x is each individual score making up the distribution, m is the mean of the distribution, and n is the number of scores. So the last one is the standard deviation. Although the variance is frequently used as a measure of the spread in certain statistical calculation, it does have the disadvantage of being expressed in units different from those of the summarized data. However, the variance can also be easily converted into a measure of spread expressed in the same unit of measurement as original score. The standard deviation, as you know, to convert from the variance to the standard deviation, simply take the square root of the variance. Then we have the measure of spread application. Choosing a measure of spread. The choice of a measure center is affected by distribution of the score. The same is true for the choice of measure of the spread. So, like the mean, the range and the standard deviation are sensitive to outliers. In cases in which your distribution has one or more outliers, the interquartile range may provide a better measure. In addition to noting the presence of outliers, you should note that shape of the distribution or normal or skewed when selecting a measure of the spread. Remember that the mean is not a representative measure of the center when your distribution of score is skewed, and that the mean is used to calculate the standard deviation. Consequently, with a skewed distribution, the standard deviation does not provide a representative measure of the spread. If your distribution is seriously skewed, use the interquartile quartile range instead. Like the median, the interquartile range is resistant to the effect of the skew and outlier. So what are the five numbers summary here? The five numbers summary provide a useful way to boil down distribution into just a few easily grasped numbers, several of which are resistant to the effect of the skew and outlier, and all of which are based on a rank of the scores. Included in the five number summary are the following: the first, the minimum first quartile, the medium, the second quartile, the third quartile, and the maximum. The minimum and the maximum are simply the smallest and the largest score in the distribution. These are not resistant measures for the simple fact that the most extreme outliers will fall at the end of the distribution, and therefore there are likely to be the maximum or the minimum scores. The three center values, the first quartile, the median, and the third quartile, are resistant measures. From the five number summary, you can easily calculate the range minimum minus maximum minus minimum and interquartile range Q3 minus Q1. The latter is, of course, a resistant measure of spread. By examining the five number summary, you can quickly determine the center, spread, range, and distribution of the quotient. So here we have an example of the five number summary. We have the maximum 1, 3, 2. We have the minimum 6, 7, and you have the median is 101, Q1 90, and Q3 110. So now we talk about box plot. As even better approach is to display the five number summary as a box plot. Graphic represent of the five number summary the first and the third quartile from the end of the box, and also a line in the box represent the median. Vertical whiskers extending above and below the box represent the maximum and the minimum score, and data from multiple treatment are presented using a side-by-side box plot. So let's see this. In this figure, for example, shows the five number summary of our Q distribution just now. We shown and display this number as a box plot. The first and the third quartile form the end of the box, which encloses a line marking the median. Then we have the two whiskers reach out from the box to mark the maximum and the minimum scores. Yeah. If you have data from several treatment or samples, you can easily compare the distribution from each mean side-by-side box plot. So you can see A is side-by-side box plot in the right here. You can often also discern the general shape of the distribution from the box plot by noting the position of the median within the box and the relative length of the two whiskers. In a systematic distribution, the median will fall close to the middle of the box, and the two whiskers will be similar in length. In a positively skewed position, the median will be pushed toward the left end or the bottom of the box near Q1. And the right or the top whisker will usually be longer than the left or the bottom one. In a negatively skewed distribution, the reverse pattern will be found. So now we talk about measures of association. In some cases, you may want to evaluate the direction and the degree of relationship correlation between the scores in the two distribution. For this purpose, you must use a measure of association. These in coming slide we will discuss several measures of association along with related topics of linear regression, the correlation matrix, and the coefficient of determination. So the first one we have Pearson product movement correlation or Pearson correlation. So the most widely used measure of association is the Pearson product movement correlation coefficient, or Pearson R. You would use it when you scale your dependent measures on an interval or a ratio scale. The Pearson correlation coefficient provides an index of the direction and the magnitude of the relationship between the two sets of scores. The value of Pearson R can range from +1 through 0 to -1. The sign of the coefficient tells you the direction of the relationship. A positive correlation indicates a direct relationship as the values of the score, in one distribution increases, so do the values in the second. The negative correlation indicates an inverse relationship. As the value of one score increases, the value of the second will decrease. So here we have an example of the spot. In this figure we illustrate a scatter plot of data showing a positive, negative, and no correlation. So here here in A it is a positive relationship, in B it is a negative relationship, but here in C there is no relationship. So the magnitude of the correlation coefficient tell you the degree of linear relationship, stretch line, or you could draw it between your two variables. For example, here positive, you can draw line here, then this is a linear regression, and here we can draw one here. But here you can see there's no relationship. If you draw a line in here or here or here, so it doesn't have any indication. A correlation of 0 indicates that no relationship exists. As the strength of relationship increases, the values of the correlation coefficient increase toward either +1 or -1. Both +1 -1 indicate a perfect linear relationship. The sign is unrelated to the magnitude of the relationship and simply indicate the direction of the relationship. So what are the factors that affect the Pearson R? Before you use the Pearson R, examine your data much as you do when deciding on a measure of a center. Several factors affect the magnitude and the sign of the Pearson R. So the presence of outlier is one factor that affects the Pearson R. An outlier can drastically change your correlation coefficient, affecting its magnitude, its sign, or both. This is especially true if you use a small number of pairs or scores to compute the Pearson R. So restricting the range over which the variables vary also can affect Pearson R. For example, if you were to examine the relationship between IQ and grade point average GPA in a group of college students, you would probably find a weaker correlation than if you examine the same two variables using a high school student. Because IQ varies less among college students than among high school students, any variation in the GPA that relates the IQ also will tend to vary less. As a result, the impact of extraneous variables such as motivation will be relatively larger, leading to a reduced correlation. So the person R is sensitive not only to the range of the score but also to the shapes of the score distribution. The formula used to calculate the coefficient uses the standard deviation for each set of scores. So you call that, you use the mean to calculate the standard deviation. If the scores are not normally distributed, the mean does not represent the distribution well. Consequently, the standard deviation will not accurately affect the variability of the distribution, and the correlation coefficient still not provide an accurate index of the relationship between your two set of scores. Hence, you should inspect the frequency distribution of each set of scores to ensure that they are normally or nearly normal before using a Pearson R. Finally, Pearson R reflects the degree of which relationship between the two variables is linear. Because of this assumption, take steps to determine whether the relationship appears be to be a linear or no. You can do this by constructing a scatter plot and then determining whether the point appears to scatter systematically around a straight line. So when the relationship between the variable is nonlinear, the person R underestimates the degree of relationship between the two variables. Pearson R is used when both of your variables are measured along a continuous scale. So you may need to correlate variables when one or both of them is not measured along a continuous scale. A specific correlation coefficient are designed for those purpose, three of which will be discussed in coming slides. We have the first one is the point biserial correlation. You may have one variable measured on interval scale and the other measured on a nominal scale. For example, perhaps you want to investigate relationship between self-rated political conservatism measured on a 10-point scale and whether or not a person voted for a particular referendum, yes or no. Because one variable is continuous and another one is dichotomous, having only two possible values, you would apply the point biserial correlation. Although there is a special formula for the point biserial correlation, in practice you can use the formula for the Pearson R to compute it. The dichotomous variable is a dummy coded as 0 for the one response and 1 for the other. So what are the factors that affect the point biserial correlation? You should know a couple of things about the point biserial correlation. First, its magnitude partly depend on the proportion of participants falling into each of the dichotomous categories. If the number of participants in each category is equal, then the maximum value of point biserial can attain its is plus minus 1, just as in Pearson R. However, if the number of participants in each category is not equal, then the maximum attained value for the point biserial correlation is less than plus minus 1. Consequently, the degree of relationship between the two variables may be underestimated. You should examine the proportion of participants using each category of dichotomous variable, and if the proportion differ greatly, temper your conclusion accordingly. So the magnitude of the point biserial correlation also is affected by the limited variation of dichotomous variable. Example, only two values possible. If the underlying variable is continuous but has been dichotomized for the analysis, example, anxiety level, specified as either low or high, the point biserial correlation will tend to underestimate the true strength of the relationship. The second, we have Spearman rank order correlation. The Spearman rank order correlation, or rule, is used either when your data are scaled on an ordinal scale or greater, or when you want to determine whether the relationship between a variable is monotonic. The rank order correlation is relatively easy to calculate and can be interpreted in much the same way as a Pearson R. The phi coefficient, is used when both of the variables being correlated are measured on a dichotomous scale. You can calculate the pi or the phi coefficient with its open formula. However, like the point biserial correlation, pi is usually calculated by dummy coding the responses as 1 and 0 and then plugging the resulting score into the formula of Pearson R. The same argument concerning restriction of range that apply to the point biserial correlation also apply to pi, only doubly so. Then we have linear regression and prediction. A topic closely related to correlation is linear regression. With a simple correlation techniques, you can establish the direction and the degree of relationship between the two variables. With linear regression, you can estimate values of the variable based on knowledge of the value of others. The following, later or in the following class, we will introduce you to a simple bivariate two variable regression. Also included are some calculation to help you understand regression, and we will do it in the tutorial classes later. So what I mean about bivariate regression is the idea behind bivariate regression is to find the straight line that best fit the data plotted on a scatter plot, and we will discuss this later. So the best fitting straight line is the one that maximizes the sum of squared, deviation of each data point from the line as measured along the y-axis. This line is called the least square regression line. At any given value of x found in the data, the position of the line indicates the value of y predicted from the linear relationship between x and y. So you can compare these predicted values with the values actually obtained. The best fitting straight line minimizes the square differences between the predicted and obtained values. So the last we have correlation matrix. If you have compared all the possible correlation among a number of variables, then you can make the relationship among the variables easier to comprehend by displaying the correlation coefficient in the table called correlation matrix. So this table here shows the hypothetical correlation matrix of 5 variables 1 to 5. The variables being correlated in the matrix are shown in the heading along the up and the left side of the matrix. Each number with the matrix is correlated between the two variables whose row and column intersect at the position of the number. For example, the correlation between variable 5 and 3 can be found by reading across the row labeled variable 5 to the column labeled variable 3. The correlation found at that the intersection is 0.06. Note that the numbers along with diagonal are omitted from the table. This is because the diagonal position represent the correlation of each variable with itself, which are necessarily to be 1. You must omit the correlations above the diagonal because they simply duplicate the correlation already given below the diagonal. For example, for correlation of variable 5 with variable 3 below the diagonal, is the same as the correlation of 3 and 5 would appear above, the diagonal. So to here, we come to the end of the class. I hope that you got an idea about how we do descriptive statistics, how we use graph and tables to describe our data and to read some the hidden information of our data. If you have any questions or you have not understand a part of this lecture, then please you can put your comment or email me personally. Thank you very much, and I will see you for the next video.